Welcome. This is the Distributed Data Infrastructure project, and this is our group. Okay, so the project goal is a little bit unique in the sense it works with something that's not as prevalent in the world, but is still important nevertheless. So this is about testing the performance of what's known as a CEPH file system, which is a distributed file system. And we basically spent this whole program analyzing how some configurations with CEPH, such as OSDs and bandwidth, affect performance. And we also compare CEPH performance with other distributed file systems as well.
So this is our hardware architecture, and we have a 8-server setup. And the first node, or the server, it provides us with the gateway, the WireGuard VPN, and also with the DHCP services. And what this does is it enables us to connect to the cluster remotely through SSH. And the second node, it contains the containers on Proxmox that we can also use to connect to the cluster as clients. And this node also contains the Slurm manager. It has our GitHub, also the MySQL database, as well as Grafana set up on it. For the nodes 3 to node 8, these are available to be integrated into our file system. And each of these nodes, they contain 3 Samsung SSD hard disks, each with a 446 gigabits, and 1 Kingston drive, which has 447 gigabits. And we also make use of 2 switches. First one is the Aruba switch, which provides interconnectivity between all of the nodes. And this supports 1 gigabit Ethernet cables. And the second switch we'll be using is the Mellanox switch, which provides the InfiniBand support. And we use this to get a higher throughput and a lower latency. And on this, we can achieve a 40 gigabit IP over IP connectivity.
Here we have the CEPH overall architecture and its components. First, we have the CEPH clients, which interact with the CEPH cluster to read and write data. Next, we have the monitor daemon, which monitors health and state of the CEPH cluster. Then we have the CEPH management daemon, which manages the metadata for the file system. Then we have the CEPH metadata server, which handles the metadata for the CEPH file system. And CEPH data is also organized into pools, which are logical storage units. And then we have the OSDs, which are our object storage daemons, which store and manage data objects. And then we have the solid state drives. And then here we have a classical file system compared to a CEPH system. This classical file system, like the network file system, can't add any more drives, which leaves it with no way to expand and needing a separate system for backups. In addition, if multiple clients talk to only one server, this may cause a network bottleneck. On the other hand, the CEPH system takes care of all these cons. And with CEPH, we can add additional nodes as well as OSDs, and backup is already built into the architecture via object replication. And finally, different clients may also connect to different nodes and OSDs as well with staff.
So RADOS and Crusher, 2 important parameters that need to be paid attention to when working with CEPH. So the flowchart here basically represents how the bottom layer depends on the top. So you have the application first, which interacts with CEPH through what's known as librettos and CEPH file system. And it sends read and write requests to RADOS, which basically stores and retrieves data. And RADOS, I already said, it's just basically responsible for storage. And also the crush, which is basically control replication under scale hashing, is basically responsible for computation of placement data. So it uses the crush map to map data into OSDs to be specific. And we have the object storage daemon, and we have the physical disk where the data is stored. And OSDs basically manage data placement and also replication and recovery as well.
The workflow is pretty automated. We first get a clean Debian install by booting into the fog installer on all the nodes. And then using Ansible playbooks, we set up and configure CEPH. We have our GitLab where we store our job files and scripts, the Slurm, which we use to schedule benchmarking jobs, and the results of the benchmarks are uploaded on MySQL. The benchmarking tools we are using are DD, FIO, and Rados bench. DD is just a basic input-output operations command, and FIO is a command which can simulate more complex IO patterns. And Rados bench is specific to CEPH, and it gives performance parameters. For redundancy, CEPH has two options. One is replication, the other one is erasure coding. In replication, the data is simply replicated in form of objects, and it's distributed among all the OSDs. The crush has the crush map, which determines how the data is distributed and replicated by the Rados. And in erasure coding, the data is fragmented and parity bits are generated. So in case of a drive failure, the parity bits are used to regain the lost data using mathematical equations like Cauchy-Good or like other XOR operations, so that we can just regain the data, but it increases the computational cost.
Yeah, for results, we can share like a couple of our primary results. We'll be compiling a full length report for our sponsors later, but here are some of the ones we can share for now. Basically, one of the first tests is just seeing how network switches impact our performance. Basically, when we use a 1 gigabit switch, it seems there's like a bottleneck based on the network bandwidth, but when we expand to a 40 gigabit IP over B network, the bottleneck seems more to be on the file system's IO rather than the file system. Next, for our second set of results, basically disaster recovery and the two erasure, like the two kinds of redundancy pools. Basically, what we can see is that for replication, we have better performance when we have a clean drive, like we have no failures. However, as hard disks begin to fail, the performance tends to favor erasure coding as the throughput has a less significant decrease.
So like any other project, there is always some work left to be done. So our main goals that we would do in the future would be to explore CEPH performance further and link it to machine learning, which is very prevalent nowadays. And we need to continue to optimize the system's performance for its application as well. We've already done some analysis on performance testing with up to 3 OSD failures. So we want to try that for more than 3 OSD failures to determine resiliency of the CEPH file system. And we need to also see how CEPH handles the failure of entire nodes with quorum voting, which is basically a concept of CEPH. So our group would like to acknowledge the people at Inversus who sponsored us for this project and helped us with giving us a lot of insight about how to approach the project, what more we can do, how we can develop it. So we also want to acknowledge our advisor, Alexei Kotelnikov, Jenny Shane, Ivan Saskar, Jacob Kolodziejski, and the rest of WINLAB staff for making this project possible. Thank you.